Hi, I'm Lorraine, a PhD student at Cornell Tech and Johnson School of Business. Today, I would like to share our recent work on privacy-preserving data-driven inventory management. Okay, that sounds a bit heavy, so let me put it more simply. Inventory management, so we're making stocking decision. Data-driven, we want to use data as an input to our decision. And privacy-preserving, we want to keep the data we use private. That's the big picture. Now, let me dive deeper in it. Using data to make decisions always carries a privacy risk. People often think of data breaches such as hacking or direct data selling. Unfortunately, that's not the only weight of threat. Even if no one breaks into a database, the decisions themselves can leak sensitive information. In this talk, we'll focus on the public decision of inventory level, which is often shared within a supply chain or visible online. Recent OM literature has highlighted that even if public inventory decisions can reveal sensitive information. Now, let me give you a few high-stake examples. In healthcare, the decisions of nurse staffing or inventory level of surgical supply can expose patient-level information. And in a supply chain, a supplier's order quantity can reveal its client's confidential data, probably to their competitors. That is, even without a direct data leak, privacy will still be at risk because the public decisions is based on some private input. And when it comes to privacy protection, people often think privacy means removing direct identifier from the database, like the name or addresses. Unfortunately, it turns out that's just not enough. And there are really epic stories about how people get identified or their data recovered in the database in the security literature. To solve this issue, we use differential privacy, which is now a widely adopted technique in the industry. And it provides a nearly as good of a protection as if your data were never included. So how exactly does the magic of differential privacy happen? Well, let's consider two almost identical databases, but one with a particular data point, that is the orange point at the bottom, and one without it. No matter what your decision protocol is, you come up with two results from the database respectively. And naturally, for most of the time, the two outcomes are different because you're using two different databases. What would differential privacy do? Well, we will add noise to it. And now your decision becomes a distribution. And what epsilon differential privacy ensures is that the differences between these two distributions at any point is bounded by a ratio e to the power of epsilon. So that means the closer these two distributions are, the stronger protection it provides, and of course, the smaller value of the parameter epsilon will be. We'll be also using this differential privacy framework to protect our public inventory decisions. That is, the research question we are looking at is how to ensure the data used to make public inventory decisions remains private. We'll be using the differential privacy framework under a new standard setup. When it comes to data-driven decision-making, there's so many ways to do data-driven optimization. And here, we focus on three main ones. Namely, the two-step estimate then optimize approach, which firstly estimate the parameters to predict demand, and then we optimize the order quantity. We also consider another two one-step methods that do both steps together. Here, local weighting, sometimes we call them weighted ERM, assign weights to each of the historical data points based on how similar it is to now. And then we just stock up based on the past experiences that shares similarities. And end-to-end learning, here more like a machine learning black box, but with the training objective function being the new standard cost. Then we'll develop privacy-preserving versions of each by injecting noise to them. Here we skip the technical detail for algorithm design, but what's more important is that even with the same privacy guarantee, the three data-driven approaches actually will end up with very different noise level. So here's the table for comparisons. To visualize this, I use traffic light colors to show performance. Here, green means the best, yellow intermediate, and red is the worst. And we show that given the same sample size, to ensure epsilon differential privacy, the two-step estimate and optimize method will perform the worst, and the one-step end-to-end learning method performs the best, as it requires the least amount of noise injection. We also show that you can't really do better than this in terms of the sample size. Here, what really surprised us is that the three data-driven approaches actually expose different level of private information due to their optimization structure. The two-step estimate and optimize method separates estimation from decision-making. So it doesn't account for how the estimation will be used downstream. Therefore, it requires the most amount of noise injection as it exposes the most private information. Okay, now with our results in hand, let's fill in our table. The next natural question to ask is, what is the right level of privacy protection to offer? That is the parameter epsilon we've been talking so far. Interestingly, this is a question often overlooked in the literature. And we find the optimal protection level and the resulting profit by accounting for customers' response. That is, with stronger protection, customer will be more likely to buy and share. Here, I'd like to briefly walk you through the trade-off for the firm. Its profit has to depend on two things, the demand and the per unit profit. Naturally, with stronger protection, the demand will go up because your customer will be more likely to buy and share. And the per unit profit has to suffer from two losses. I just show you that the three methods actually differ in the losses from privacy protection. But they also naturally differ in the loss due to finite sample size. And the optimal protection level, epsilon, will then be determined by this trade-off. When we compare the optimal solutions across the three methods, something pretty impressive shows up. It ends up that end-to-end learning approach will provide the strongest protection, which is good for the customer. It also achieves the highest profit, which is good for the firm. And all of that happens thanks to the fact that the end-to-end learning method requires the least amount of noise injection to ensure a same privacy level. We also find that privacy protection doesn't necessarily has to come at a cost. When we compare the optimal solution to the benchmark where no privacy protection is offered, firms are actually better off. Next, I would like to show you some numerical results to see the actual improvement. We applied our proposed differential privacy algorithms to a real-world e-commerce dataset. Since the data itself doesn't tell us how much customer values privacy, we then vary the privacy disutility on the x-axis. And this picture shows that both of the one-step methods provides much stronger protection. That is, smaller epsilon on the y-axis. And typically, firms will choose 3 to 6 times stronger protection than its two-step counterpart. And when we look at the resulting profit, when customers really care about privacy, that is the place that I highlight at the far right of the graph. The two-step methods actually performs no better than the benchmark, where no protection is offered. While the one-step methods, and especially the end-to-end learning one, can still boost the demand by up to 40%, which is pretty impressive. Okay, now let's recap. What did we learn so far? If we don't think about privacy protection at all, both of the two-step and one-step methods has their merit, and one might be better than the other, depending on the context. But once we introduce privacy protection, the story changes. Using one-step method, and especially the end-to-end learning one, will give you a stronger protection and also achieve a higher profit. This implies that If a firm is currently using a two-step decision protocol and is considered providing privacy protection, the firm should not simply use the privacy-preserving version of the two-step algorithm. Rather, switching to a one-step end-to-end learning, privacy-preserving algorithms might be the best way to go. Last but not least, thank you for your attention, and feel free to check out our paper if you're interested in more details.